All right, here we go. Well, this is Cournot lecture part 3 with asymmetric duopoly. And we're going to left up some of the results for the symmetric cases here as reference. We're going to do a simple example of the asymmetric case. I'm switching to blue here to denote the new work. And we're going to impose that P is equal to 12 minus Q, our inverse demand. And we'll stick with constant marginal costs as we had in this first case over here, but different marginal cost for each firm. So firm 1 will have marginal cost equal to 1, and firm 2 will have marginal cost equal to 2. Should be easy to remember. Firm 1 has 1, firm 2 has 2, right? And this is essentially the only aspect where we would have asymmetry here, right? Because as long as the firms are producing essentially the same good, which then a Q is a Q is a Q, right? They just add their two quantities together to get the total quantity in the market, which means that this inverse demand applies to both of them equally. We can imagine settings where the products from different firms are not necessarily identical, but that is more of the monopolistic competition or product differentiation setting that we are not trying to capture in this Cournot model, right? So the units that they're producing are effectively the same. It's just one is firm coming from firm 1 and the others are coming from firm 2. Excuse me. And so if there's going to be any difference between the two firms, it's going to come in through their cost function, right? So for this example, we'll just allow that we have these constant marginal costs, but instead of them both being equal to the same C, firm 2 has higher marginal costs than firm 1. We'll start from the same place, right, where we maximize firm 1's profit. So we're maximizing 12 minus Q times Q1 minus, marginal cost is equal to 1, so that's really minus F1, their fixed costs, minus their cost of production, which is going to be 1 times Q1, right? This marginal cost implies a fixed cost plus just Q1 as the total cost for the firm. All right, so taking a derivative of that, we will get our marginal revenue equal to marginal cost condition. Sorry, taking a derivative and setting it equal to 0. And so that is going to be 12 minus 2Q1 minus Q2 equal to 1. Going to do the calculus of that to prove it to yourself, right? I just know this from familiarity with our marginal revenues, which is this side, and marginal being equal to marginal cost, right? So now, to get our best response function for firm 1, we want to solve this for Q1. We have 2. Q1 is equal to 11 minus Q2, right? Now, thus, Q1, or firm 1's best response to Q2, is going to be BR1 as a function of Q2 is equal to 11 halves minus 1/2 Q2. Now for firm 2, is going to be the same condition here, right? Except for their marginal cost is equal to 2. So note that we are getting the exact same best response function as you have here if you put in the values that we've imposed, right? Where B is equal to 1, C is equal to 1, and A is equal to 12 for firm 1. For firm 2, A and B are still 12 and 1. Now C is going to be equal to 2. So our best response function for firm 2 that you can derive is I left that as 10 halves just to highlight the similarity here. Obviously, that is equal to 5. And so now what is the next step if we actually want our Cournot equilibrium, right? Let's recognize here that this best response is the choice of Q, or Q1C, right? Same thing here. And we're solving for the point where these are simultaneously true. One way that we could visualize what we're doing here is to be able to graph this, right? Which would be, if we've got Q2 up here and Q1 down here, so I'm putting this in the Cartesian space of the two firms' outputs, right? Then this best response for firm 1 is this quantity as a function of that quantity, and this best response for firm 2 is this quantity as a function of that quantity. This is the one that is our typical way of writing one function as in terms of another and graphing it, right? Because Q2 is on the y-axis, just like y equal to f of x, right? Y up here and x down here. So this function is already in the form to see that it is 10 halves or 5. We'll say that's right there. A straight line with slope -1/2. So actually, that's not quite shallow enough. Let's redraw that a little bit lower. Since that is an intercept of 5 and a slope of -1/2, it goes from 5 to 10, right? And so that's the best response function graphically for our firm 2. Now firm 1 is Q1 as a function of Q2. So if I wanted to graph this in that space, really I would resolve it for Q2, in which case it would be, let's see, 11 minus 2Q1, right? So that function there, graphed in this space, starts up here and comes down with a slope of -2, right there. Reason for this exercise is to highlight what our best response functions actually are when we frame this in that game theory type framework, right? It's just saying for any value of, let's denote these so that we don't forget which is which. This is best response for firm 2 to a quantity by firm 1, and this is the best response for firm 1 to quantity choice by firm 2, right? So this is saying as Q1 increases, firm 2 is going to want to decrease their quantity from 5 to smaller and smaller quantities, right? Is going to be their best response to a particular choice of Q from firm 1. Now, at the same time, firm 1 is never going to want to actually have a quantity greater than 5.5, right? Because this is their best response to any particular quantity from firm 2. So the point at which they're both playing their best response is going to be some point like this, where we're going to have a Q1C and a Q2C, and visually, because this is roughly proportional in the right ways, the Q1 that we'll find here will be greater than the Q2 because firm 1 has a lower marginal cost of production. And the math to do that, right? Because now we cannot, because the firms don't have this symmetric condition where their problems are identical. Now we are going to substitute one into the other in order to have them simultaneously true. You could also do other forms of solving systems of equations, but we're going to go with this one. So I have Q1 is equal to 11 halves minus 1/2 Q2, and Q2 is equal to 5 minus 1/2 Q1. So I'm going to sub this Q1 function in to this second equation. So that's 5 minus 1/2 times 11 halves minus 1/2 Q2. So we got 5 minus 11/4 plus 1/4 Q2. And that plus 1/4 Q2, we're going to subtract to the other side in order to solve for a closed form solution on Q2. So we have 3/4. Notice some of the similarity to the solution that we derived over here. 3/4 Q2 is equal to 5 minus 11/4. I am going to leave that form for now because this is going to change things up a bit here. So we've got 5 minus 11/4, and then Q2C for Cournot is going to be 4/3 times 5 minus 11/4. That is 20/3 minus 11/3. It's equal to 9/3, or just 3. Cool. I'm going to scratch this now, right? We just solved essentially for that being 3, and now this I know is not going to be equal to the same value, so I need to quite simply take this Q2C equal to 3 and put it into this here. Q1C is going to be equal to 11 halves minus 1/2 Q2C, which is 11 halves minus 3 halves. 11 minus 3 is 8. Q1C is equal to 4. So, math, fairly straightforward. Carrying around a couple of fractions here, come out with nice set of round numbers on this. Note that they are different from, slightly different from what we would have had over here with our, say we impose the lower marginal cost for both firms, right? And this inverse demand in this setting here, then we have 12 minus 1 is 11, and 1/3 of 11 is something that is less than 4 and greater than 3. And we can also show, right, because here QC is equal to 7, and over here 2 times the 11/3 is 22/3, which is slightly greater than this 7 here. Essentially, the total output would be greater simply because if both firms have marginal cost equal to 1, then the cost of production is lower. So we should expect, right, that the overall output would be greater, and that the firm with the lower marginal cost, firm 1, should end up producing more, right, when they maximize their profit than the firm with the higher marginal cost should. Right? So intuitively, all of these pieces should fit nicely together. Note that with asymmetry, it becomes difficult to conceptualize what the efficient outcome is here, right? Because, well, not that difficult, but trickier, because if you recall from the previous part of the lecture, if this is marginal cost and this is our demand function, we can find a socially efficient outcome by setting them equal to each other, right? But if we have 2 different firms with 2 different marginal costs, then which one should we use for deciding what an efficient outcome is? We would, with firm 1, I'll just go with firm 1 and firm 2. With firm 1 having a lower marginal cost than firm 2, we would want firm 1 to produce all of this output in order to produce it in the most efficient manner possible, right? Therefore, the efficient outcome would be with marginal costs equal to 1, and so demand equal to that marginal cost would be 12 minus Q equal to 1, Q E equal to 11. Right, so the efficient level of output would be 11, but that's imposing that firm 1 produces all of that output. And that's specific to this case where both firms have these constant marginal costs, right? Which, recall, is essentially our condition for a natural monopoly, where if there are any fixed costs and there's constant marginal costs, that means there are economies of scale for any level of production, and therefore a single firm can produce any given amount of output for less than multiple firms producing that same amount of total output. that changes, right, if we instead model our asymmetric firms as having increasing marginal costs, then it is no longer the case that it is always cheaper per unit for firm 1 to produce the output, because if firm 1 is producing this many units of output, then their marginal cost of production is greater than that of firm 2 to produce the first, second, third, whatever number of units of output there, right? So in the case where we have multiple firms with increasing marginal costs of production, it becomes much more complicated to solve for what the efficient output level is, which is why we skirted around that in the previous part of the lecture as well, and stuck with just constant marginal costs. The thing to keep in mind when we discuss duopoly, oligopoly, anything with constant marginal costs, is that it will always be most efficient for a single firm to produce with constant marginal costs, right? Because since that cost is fixed, one firm can produce at the same marginal cost as the other firm at any level of production, and so the second firm just adds an additional set of fixed costs that do not necessarily need to be incurred in the market. All right, I'll talk a little bit more about that in the next lecture, where we will expand from the Cournot duopoly setting to a third firm, and possibly even think about more firms.